In this video, we're going to use some examples to demonstrate the application of the Nyquist stability criteria. Now, the previous video introduced the criteria and showed that you could assess closed-loop stability given the Nyquist diagram of the open loop, and you'll notice keywords there were assessing closed loop based upon open loop. Now, this video will give a number of examples showing how you can use the criteria to do this, and therefore to analyse feedback loops. Later videos will look at how we can use this information for design. So just a reminder of the background. If you define NO to be the number of open loop right half plane poles, NC to be the number of closed loop right half plane poles, and NQ to be the number of clockwise encirclements of the -1 point, that's by the Nyquist diagram, then you get this formula here. NQ plus NO equals NC. Now, these bits in brackets are just to remind you that this has originated from a formula of the type PC over PO, so the closed loop poles are in the numerator and the open loop poles in the denominator. So what do we get from this formula, NQ plus NO equals NC? If a system is open loop stable, so NO equals 0, then the closed loop is stable if and only if the Nyquist diagram has no encirclements of the -1 point. If a system is open loop unstable, then the closed loop is stable if and only if the Nyquist diagram has NO counterclockwise or anticlockwise encirclements of the -1 point. And we will demonstrate this through a number of examples. So first example, 3 over S plus 2. So the first thing you need to do when you're using the Nyquist stability criteria is complete the Nyquist diagram. So let's do that first. There we go. The next question is to ask yourself, how many encirclements of -1 have we got? Well, -1 is all the way over here. It's clearly not inside, so we have NQ equals 0. Next, how many open loop right half plane poles have we got? Well, you can see the pole, we've got S plus 2, which is left half plane, so clearly NO equals 0. There are no poles in the right half plane. Then we use this formula here, NC equals NQ plus NO, and we get NC equals 0. So therefore, because NC equals 0, this system will be closed loop stable. Example 2, 3 over S plus 2, S plus 1. And again, we'll use the same procedure. First, complete your Nyquist diagram. So there we go. Completed our Nyquist diagram. Ask yourself, is -1 point inside it? Are there any encirclements? And clearly here it's not. So we have NQ equals 0. Next step, ask yourself, do we have any open loop right half plane poles? Well, clearly both of these poles are left half plane, so NO equals 0. Apply our formula, and so we get NC equals 0. So again, this system will be closed loop stable. Two more examples, just for completeness. Now, I'm not going to go through all the steps here. You can see the -1 point is here. You can see that in both cases, NO equals 0, NQ equals 0, and therefore NC equals 0. And so they will be closed loop stable. Now a more challenging example. Use the Nyquist stability criterion to establish the range of gains, the gains being this value here, k, for which the following is closed loop stable. So you see you've got the Nyquist diagram, and now we want to ask ourselves, is this going to be closed loop stable? And we're going to do this in a few steps so you can get the generic procedure. Right, first of all, let's note the obvious, NO equals 0. You'll see that all the open loop poles are at -1, they're in the left half plane, and therefore in order to be closed loop stable we must get NQ equals 0. So that's our target, no encirclements of the -1 point. First then, let's consider k equals 1, just because that's nice and simple. Well, you'll notice we've marked over here the -1 point, and clearly in this case NQ equals 0, which is what we wanted, so we are closed loop stable for small k. And you can see that if I was to make k even smaller, I could make the plot do something like this. There would still be no encirclements. So for small k, no encirclements, I'm closed loop stable. What happens, however, if I make k a bit larger? And you'll see here I've done k equals 15, and now you'll notice the -1 point is inside here. So what have we got? We've got an encirclement here and an encirclement here. So clearly NQ equals 2. We have 2 encirclements clockwise direction, and therefore we're going to have 2 closed loop right half plane poles if k is 15, or indeed if k is larger than this, because if I was to make k larger and I use black, you could make the Nyquist diagram do something like this, and obviously you've still got 2 encirclements. So here's the question: what do we mean by small and large k? We've said for small k we're closed loop stable, for large k we're closed loop unstable. So how do we distinguish between small and large? Well, the key thing, the key factor that's going to come in here, and hopefully it's obvious, is this intercept in here. This intercept with a negative real axis, because that determines whether the -1 point is inside those loops or outside those loops. So the next step is to find that intercept. So the intercept is defined by the argument of g is -180. So let's follow this through and see what we get. The argument of g is -3 times the argument of s plus 1. You can see that because there's an s plus 1 cubed in the denominator, which is -3 tan to the -1 of omega, and we're going to set that equal to -180. So given that, you will immediately see that omega is going to be √3. Now, having done that, I can find out the magnitude of g. So the magnitude of g at √3, this is going to be k over the square root of 3 plus 1 cubed. I've done that quite quickly, but obviously you can check this more slowly if you need to. And so what you're going to get is k over 8. So the intercept, if I go back to this previous slide, or perhaps oh, that's not helpful. This intercept is at k over 8, or minus k over 8, because obviously it's on the negative real axis. Okay. And now, where do we want this intercept to be? So if I do my little sketch over here, just so we can see what's going on, if this intercept here is at minus k over 8, and where do we want the -1 point to be? We wanted it to be here, so that it wasn't inside and we didn't get any encirclements, and therefore we require k must be less than 8. So if k is less than 8, then the -1 point is to the left of that intercept, and we have no encirclements. If k is bigger than 8, then clearly the -1 point is inside, and we have 2 encirclements. So here's another question. For what value of k is g closed loop stable? And you'll see we've given you a system up here. So what process do we need to go through? First of all, we need to sketch the Nyquist diagram and determine the encirclements for small and large k. And closed loop stability requires we have no encirclements, as the system is open loop stable. Now, the number of encirclements may well change with k. We saw that with the previous example. So if the Nyquist diagram crosses the negative real axis, and consequently, in that case, this intercept is important information, because as that intercept changes, the number of encirclements may change. Now, we're only going to consider positive values of k, but you will find there are questions in examiners who want you to look at negative values of k as well. I'm not going to dwell on that. So then, first job, sketch the Nyquist and hence determine the encirclements. So first, the way we've done this in the past is we've said let's do a crude bode sketch to see what's going on. Corner frequency at 4, flat gain up to 4, then a slope minus 80 decibels per decade. I'm not too worried about the numbers. We can put those in later, but clearly at steady state we had 100k over 256. What about the phase? Well, we've got 4 factors in the denominator, so we're going to go down to minus 360 degrees. All of these are at the same corner frequency, And so what we can do by inspection is we can show that we must go through minus 180 degrees, okay, at that corner frequency just from symmetry. If you don't believe me, you can check this for yourself. What's the Nyquist diagram going to look like then? Well, it's going to start over here at 100k over 256. I might not be too worried about that. And then it's going to circle right round like this. Okay, I've perhaps made that a little bit too small, but you can see the key point, and what we're asking is where's this minus 1 point? Is it here, or is it here? So we've got NQ could be 0 for this scenario, or alternatively, NQ could be 2 for this scenario. And so what we're going to need to do is calculate this intercept point in here and find out, is it to the right or to the left of minus 1. So let's do that then. Let's find the intercept with the negative real axis. Now we already know that omega equals 4 implies arg equals minus 180. We did that on our boat diagrams. And therefore modulus of g of j4, we can substitute this frequency straight in, is going to be 100k over, now if you put 4 into j omega plus 4, the modulus is 4 root 2, but this is to the power 4, so you're going to end up with 256 times 4. Now what we want is we want the modulus of g of j4, we want it to be less than 1. And therefore we need k to be less than 4 times 256 over 100, which is less than 10.24. And what you'll see we've said at the bottom is let's try this on MATLAB and see if our algebra indeed has worked. So let's do that now. So if I go to MATLAB, you'll notice I've entered this system into CISO tool, so you can see the different plots. So what have we got? We've got a compensator of 1. You can see there's the root loci. Here's the boat diagrams. Here you'll notice minus 180 degrees corresponds to 4, as we suggested. There's the closed loop step responses with stable for k equals 1. And here's the Nyquist diagram, and you'll see minus 1 point all the way over here. No encirclements for c equals 1. So now let's increase the c and see what happens. We see the Nyquist diagram has got bigger, but still not gone round the minus 1 point. Plots have got oscillatory, but we're still stable. Let's go up to something like 9. The Nyquist diagram's got bigger, but still not gone around the minus 1 point. The encirclements are still 0. Closed loop response is not looking so good anymore, but we're still stable as expected. Let's go up to 10. And what do you see? Again, we're still stable. You can just about tell that the minus 1 point is still outside the Nyquist plot. No encirclements. Everything's fine. So now let's go to 10.24, which we said was the critical point. And what do you see now? You can see the Nyquist diagram has gone through the minus 1 point. We're on the borderline of stability. And what do you see from the closed loop step responses? Permanent oscillation. If I go above 10.24, let's try something like 10.5. What do you see now? You'll see, if I zoom, if it allows me to zoom a bit better, not easily, you'll see we're unstable here. If I was to zoom on this diagram, I'll use this magnifying glass, and then you'll see that we've gone round. It's not particularly clear, but you should be able to see that we've gone round the minus 1 point there. You can just make out that the plot has gone round it, so we've now got 2 encirclements. Some other examples then. Open loop, unstable example. Use Nyquist to assess the stability of the system here. K, s plus 0.1 over s minus 1, s plus 0.2. And we've given you the complete Nyquist diagram here. And we've also marked for you this intercept point, because that could be useful. We've said the intercept with a negative real axis is often relevant information. And there it is, minus 0.5. We want to know what range of values of k makes this system stable. Well, clearly, what have we got at the moment? We've got one open loop right half plane pole, NO equals 1. But with k equals 1, we've got NQ equals 0. And what we want, if you remember, is we want NQ equal minus NO. That's our criteria to be stable. So we need a counterclockwise encirclement. And at the moment, we've got no encirclements, and therefore we will be closed loop unstable. And indeed, you'll see it says here, if k is less than 2, then this point here is going to stay to the right of the -1 point, and we will remain unstable. If k is bigger than 2, then what's going to happen if I take k bigger than 2 is this plot is now going to do something like this. So that's for k greater than 2. And now what do you see? If you put the direction of the arrows in, that's important, you see you get a counterclockwise encirclement. NQ equals -1. And therefore now NQ does indeed equal minus N0, and you will be closed loop stable. So there's the conclusion. Okay, if k is bigger than 2, you're closed loop stable. If k is less than 2, you're closed loop unstable. And there's a root loci, just to demonstrate the point. What does the root loci tell you? If you look over here, you'll see for small values of gain, you've got a closed loop pole in the right half plane. But as you increase k, there comes a point where that pole moves into the left half plane and you become closed loop stable. So in other words, you need large gain, okay, for closed loop stability. And that's the same message you got from Nyquist. It told you k less than 2, unstable, k bigger than 2, stable. Different example then. Is this system closed loop stable? Now what do you notice? We've got not just one, but we've got 2 right half plane poles in the open loop. So in other words, if I put it here, we've got NO equals 2. So what do we require? Well, let's start with what we've got in the first place. We can see NO equals 2, but for this value of gain, we've got no encirclements, and the other thing is, there's no intercept with the negative real axis. If I blow this diagram up and blow it up further and further, what you will see is there's no way I can get an encirclement of the -1 point. And therefore NQ equals 0 for all positive values of k. And therefore we're always closed loop unstable. We can't do anything about it. And if you look at the root loci, here's the root loci, what do you notice the root loci tells you? It tells you that for all positive values of k, you stay in the right half plane. You cannot stabilize this system. So you see we've got the same answer from root loci and from Nyquist. What about this example then? Is this system closed loop stable? So again, you'll see we have a single right half plane pole in the open loop. But if you look at this Nyquist diagram, you will see that we have NQ equals -1. We have a counterclockwise encirclement. So you're looking positive. You're saying this looks good. And so what do we see is that NO equals 1, NQ equals -1, so NC equals 0 as long as k is bigger than a half. And why do I say bigger than a half? Because you'll see the intercept with the negative real axis is at -2. If you reduce the gain, then you could make this Nyquist diagram do this. And if you were to do that, you would lose your encirclement. So you still need k to be large enough to get this encirclement. And again, if you look at the root loci, you will see you get the same insight. The pole starts in the right half plane, and as you increase gain, it moves into the left half plane. So you're not stable for small gain, but you are stable for large gain. And there's a general note. Open loop unstable systems can only be stabilized with high gain. That's a general observation. So some conclusions. We've given a number of numerical examples of applying the Nyquist stability criteria to open loop systems. Notably, we haven't done any with integrators yet. And we've shown by example that the number of encirclements and thus closed loop stability can change with the gain k, but it only changes if the Nyquist diagram crosses the negative real axis, because then the number of encirclements can change. We've reminded students that you should use other tools, such as root loci, to check or reinforce your findings, because that will give you confidence. I've got the same insight from 2 different methods. I must be right. And we've also reminded you that it's a good idea to go and use tools like MATLAB to check what you're doing and see, have I got the same result from MATLAB? Because again, if I have, I'm likely to be doing things correctly.